Get lost.
Start video.
And that's it. And I don't have to log in or give passwords or anything. By Jove, I think we've got it. Jolly good.
Nobody's on yet, but it's still a little bit early.
Oh yeah, we're 15 minutes early. You showed me, you see that share screen thing?
Mm-hmm.
You showed me a way of clicking on that and maybe putting in my whatever you call it, my stick. And
I'll have to show you again. It's all not work.
It's right there.
Yeah. All right, I'm gonna go to work.
Okay, buddy. See you later.
See you later.
That looks really good. Well, I wonder if we have any customers yet. Let's see. Participants. Nope, nobody. Nobody showed up yet. I guess we're early. Okay, well, we'll just wait till they show up. Let's see what we're going to study today? How about the first law? First law. First law. What else can we study? Specific heat. And what else? Enthalpy. Well, those are three very big topics. Hey, look, I think I've got a customer. No, it's not. It's Roxana. Hey, Roxana.
Hi.
I'm glad you joined us. Right now. Oh, hey, there's another. Megan. We've got Megan too. Yay. So we're doing, hi, Megan. So we are slowly coming into the classroom now. All right. Well, while you two are logging in, did you have any questions for me? Listen, wait a minute. Am I supposed to? I'm probably supposed to pin this. Let me try that.
I actually did have one question.
Okay.
On,
Is that Megan talking?
no, Roxana.
Roxana. Okay. Go ahead, Roxana.
On the exam, there's
Yeah.
a 1B.
Uh-huh.
You tell us to find the temperature with this value of pressure, and then
Yes.
this specific volume value. But the
Yeah.
specific volume, it says 1,300, and I feel like that's a little bit too high. So
Yeah,
I
it's
was wondering if,
supposed to, Roxana, it's supposed to be 1.300.
oh,
Does
okay,
yours
okay.
does yours say 1,300?
Yeah, it's missing the point.
Well, that's wrong. It's 1.3. I need to
Okay,
tell everybody that. Thank you
okay,
for
thank you.
bringing that up. I think you'll be okay if you'll change that to 1.3.
Okay, I will do that. Thank you.
Yes. And remind me, Roxana, before we're through, to tell everybody that. There was another wonderful student that emailed me with the same concern, and I emailed that person back. How about anybody? Hey, we have another customer, Stuart. Welcome, Stuart. Any other comments or questions? No extra charge. We have 2 minutes before class officially starts. And you can ask me a question if you want.
I had a question about the test
Yeah.
on 1.B. Is that
Yeah.
supposed to be 1,300 foot cube per pound?
I guess I goofed up on that, Stuart. Change that to 1.300, okay? If you'll do that, you won't have any trouble. I thought I'd changed it, but I guess not. It's just not easy getting a college degree. Have you noticed? There's always some little glitches along the way. Hey, looky here. We've got Spencer and Mohammed and Cameron. We're doing great. We got 7 people so far. And I've got 1 minute before class starts. You have 1 minute to ask me an extra question if you want. Hey there, Spencer. Yeah, there he is.
I have a question.
Go ahead.
I sent you an email on Monday
Uh-huh.
with a question about the homework.
Yeah.
I was wondering if you'd seen that. I hadn't gotten a response.
Oh, gee, Spencer, I'm so sorry. I don't remember if I'd gotten that, but I'll look at it. Can you tell me what the problem was?
It was basically I wanted to make sure I was using the right process. I thought I figured it out, but I wanted just to see if there was a specific spot where I went wrong.
Well, yeah, let me look at that and get back to you.
All right, thank you.
I will. Well, let's see. I've got a pretty good class now, so I think it's time we should get started. We have some huge topics today. The first law of thermodynamics, we'll talk about that. And then we'll talk about specific heat and enthalpy. Those are our topics. Well, let's start with the first one then. The first law of thermodynamics. It's probably the most important topic that we study. It's the most important, and it is in your book. It's on page, let's see if I can find it here. I'm trying to find it. Yeah, there it is. I see it. Well, it's in my book on page 60. It's probably all over the place and many other places, but here it is. Now that's how they write it in the book. It's on page 60. Now they don't specifically say that's the first law of thermodynamics, but that's what it is. Well, that's the chapter. The chapter is the first law of thermodynamics. This whole chapter is centered on that equation. And let's talk about each term here. And this here is total energy. With a 2 there, that's your state 2. That's your final total energy. When you have a process, you go from state 1 to state 2, and state 2 is your final total energy. And it consists of internal energy, kinetic energy, and potential energy. And by this, they're talking gravitational potential energy, which you guys are familiar with that. It's MGH. Only we use H for enthalpy, so they use Z for height instead of, I'm sure when you learned gravitational potential energy, you learned it as MGH. You learned it as MGH. But see, we use H for something else, so they use Z for height. That's okay, it's just a variable. And kinetic energy is our old friend that we know and love. 1/2 mv squared. But they make the V a little different because, see, we already have a V. See, we already have a V for volume and a little v for specific volume. But see, this V here is velocity. You guys know that. Kinetic energy is 1/2 mv squared. So they make their velocity a big, well, it's sort of a bold-faced V. And this thing here, this is internal energy. And really what that amounts to is your temperature. The hotter something is, a quantity of mass, the hotter it is, the more internal energy it has. It has to do with the molecules vibrating, okay? And like with water, if you get water hotter, the molecules vibrate faster. If you can get water hot enough to boiling, they vibrate so fast that some of them will leave the surface of the water and go out into the atmosphere as water vapor. So this is called internal energy. And it has to do with the temperature. If you go to the tables, you'll find little u. See, all of these can have little letters. You can have little u. See, what you do is, if you divide everything through by m, if you take and divide everything through by m, that's okay, algebra students. You haven't violated any algebra by doing that. And then see, what you'll get is a little e equals a little u plus this bold-faced v squared over 2 plus gz. And this has a name. It's called specific total energy. This one here has a name. It's called specific internal energy. This quantity has a name. It's called specific kinetic energy. And this quantity here has a name. It's called, I'm having all the fun here. Let's start with Stuart. Stuart, unmute and tell me the name of this quantity right here. Go ahead, Stuart. Earth calling Stuart. Earth calling Stuart. Come in, Stuart.
I'm not quite sure.
That's okay. That's why I need to know where you are. Let me go back over it, Stuart, and you're going to get this. This here is called total energy. When you divide by the mass, you get specific total energy. This here is called internal energy. When you divide by the mass, you get specific internal energy. This here is called kinetic energy. When you divide by the mass, you get specific kinetic energy. Now, Stuart, you can do this. This is called potential energy. When you divide by the mass, this is called what, Stuart?
Specific potential energy.
You got, by Jove, you got it. Jolly good. It's specific it's specific gravitational potential energy. Stuart got it. And I bet the rest of you got it. Okay, well, great. Any comments or questions so far? Well, on a lot of the problems that we do, nothing is moving. We're just like you have a piston cylinder on a laboratory table and you're, I don't know, heating it up or something or compressing it, but it's not moving. So this is zero. So you can forget it. For probably 90% of the stuff we do, it's not moving. So you can forget it. Now, potential energy, gravitational potential energy. If you had like a piston cylinder sitting on a laboratory table, it's not going upstairs, it's just sitting there. So it's the gravitational potential energy is not changing any. And we're really interested in the change in these things. Can you see that when you subtract this, you're getting a change? In fact, the way I write it is like this. That delta in mathematics means change. See, this is final minus initial. Delta, that's what delta always means. Delta always means final minus initial. And for 90% of the problems that we do, there isn't any change in the kinetic or potential energies. So here's the equation that we'll wind up using most of the time. However, there are situations where you have to include these other things, and we'll try to talk about them. Now, the topic right now, for those of you that maybe had to go get your cup of coffee and you come back and what's he doing now? We're talking about the first law of thermodynamics, and that's it. You're looking at it. Only if you divide through by mass, what you'll get is and I won't put the little 1, 2 on there. I'll just do it like that. And in fact, if you can throw out the kinetic and the potential terms, you don't need them. What you're left with is that. And that's what we'll use probably 90% of the time. Now let's talk about the name of this. I'll see if Spencer, I'm gonna pick on Spencer now. Spencer, can you tell me the name of that right there? That delta little u. Spencer, go for it.
That's the change in specific internal energy.
That's it. Good going, Spencer. Good going. It's the change in specific internal energy. And here, I'll write it out for you. It's the change in specific internal energy. That's what that is. And the change, internal energy depends on the temperature. I was telling you guys that, and about how fast things vibrate. Yeah. Now this here is your heat transfer per mass. See that big Q? That big Q is heat transfer. Let me write that for you. It's heat transfer. Yeah, when you divide by mass, that little q is it's heat transfer. Well, some people could call it specific heat transfer. In fact, I think your book does. Your book calls it specific heat transfer. I really don't like that name personally. I'd rather you called it heat transfer per mass. That's what I prefer. It's heat transfer per mass. The reason is we're going to study something in a few minutes called specific heat. And specific heat is different than specific heat transfer. I need to, hang on, I need to plug in my battery thingy here. I'm getting mighty low. So let me plug in my battery just a second. Oh, okay, there we go. We've got the battery plugged in there. That's better. And I was telling you about these terms here, really about this equation here. This is really what I'm talking about right now. And this is your heat transfer per mass. This big Q is heat transfer. The little q is heat transfer per mass. I think you guys need to know the names of all this stuff. What good is it having all these little Q's and W's and everything if you don't know what they are? I think it's important. You got to know the names of this stuff. Okay, now you got to know this, that heat transfer is positive when there's a heat transfer into your system, your quantity of mass that we're talking about, like in your piston cylinder, for instance, or maybe you had some oxygen in a tank and you had some heat transfer into the tank. That's considered positive. But if the heat transfer is out, going to the environment, that's negative. So heat transfer is positive if it's going in, and it's negative if it's going out. And another thing you need to know about heat transfer per mass, that's what that is it always goes from hot to cold. For instance, if you go out in the wintertime and get all cold and then come inside and shake hands with somebody inside that's already warmed up, there'll be a heat transfer from the warm person's hand to your cold hand. Heat transfer is always from hot to cold. The heat doesn't transfer from your cold hand to make the warm person's hands warmer. It doesn't work that way. Mother Nature doesn't work that way. The way Mother Nature works is the person with the warm hand, there's a heat transfer to the person with the cold hand. The person with the warm hand, their hand gets colder. And the person that has the cold hand that just came in from the icy snow, their hand will get warmer. That kind of makes sense, doesn't it? Now you need to know something though. Air conditioners do just the opposite. And refrigerators and freezers, they do just the opposite. They transfer heat from the cold, like inside your refrigerator. Inside your refrigerator, it's cold. You're keeping your milk cold, your eggs cold. Everything in there is cold. But the refrigerator transfers heat from that cold stuff to your warm kitchen. See, that's not, Mother Nature doesn't like that. You can do that, but there's a catch. You have to pay for it. You have to plug that refrigerator in, and you have to pay a PSO for the electricity to do that. Heat does not by itself transfer from cold to hot. It's always hot to cold. Now, this little term here is work per mass. Now, if you want to call it specific work, that's fine. I think the book calls it that. I think I prefer work per mass, but that's okay. And it's positive if you expand. Expansion work is positive. I think I've told you that. But compressive work is negative. If the environment does work on your system, that's considered negative. But if your system does work on your environment, that's considered positive. Okay, now you think that over while I write down the roll here. I'm just curious who tunes in and who doesn't tune in. You think that over and you ask me anything about it if you like. This is the 10th. And we've got Mohammed and Megan. What about Parker? Is Parker in our list? I don't see him. Not yet. Stuart. How about Bear? Is Bear in there? Yep. Aubrey, Roxana, Cameron, Spencer. Okay. Do you have any question about this first law of thermodynamics for me? Okay, well, let's talk about the units for a minute, and then we'll move on to the exciting world of specific heat and then enthalpy. Make a little room here. Now the units on this are kilojoules per kilogram. I'll put them in brackets. And these are kilojoules per kilogram. Everything is kilojoules per kilogram. And this here is kilojoules per kilogram. That's nice because when you add or subtract, you have to have the same units. You can't add different units. That doesn't work. Now, in the English engineering system, this here is BTUs per pound mass. BTUs per pound mass. Same thing. BTUs per pound mass. There you go. And see, we have tables. You can look that up in the tables. Any comments or questions on any of that for right now? Well, let me ask you some stuff. We'll pick on Mohammed. Mohammed, on what's the word on whatever? What do they call that? Unmute. That's the word. Mohammed, unmute and tell me. Now, this is the most important equation in our whole course. I want to know, Mohammed, I want to know the name of this equation. What is the name of this equation, Mohammed? Go.
I think the first law of the thermodynamics.
Yay, good, proud of you. That's exactly right. Good going. Of course, so is this. It's the same thing. It's just different ways of writing it. Now, you guys do need to know something. We study basically two different kinds of systems in this course. Control masses and see this equation is for control masses. There's another version of the first law for control volumes. See, this is what we're studying right now is chapter, I don't know, what chapter are we studying? Chapter 3. We are studying chapter 3. Well, chapter 4, I'm not going to write the first law, but we're going to get to it all right. It's different. Because, see, chapter 4 is control volume. That's things like, I don't know, a pipeline or a turbine, things like that. See, a pipeline or a turbine or 100 other things, they have mass coming in and mass going out. See, like a steam turbine, for instance, has steam coming in, and it can be steam going out, or it could be a saturated mixture going out, but it's got mass coming in and mass going out, whereas a control mass does not. It's like a piston cylinder. Whatever mass you got in that piston cylinder, you're stuck with it. It doesn't get out, and no new mass comes in. And the first law is different for control volume. See, I write that as C dot V. You just need to know that we study two different kinds of systems, control masses and control volumes. See, this is called control mass. This is called a control volume. It's unfortunate that they named it that. Some books call it an open system. I think I like that name better because students see this control volume, they think, oh, well, that means the volume stays the same. Well, it might stay the same, but then again, it might not. But the volume can actually change in a control volume. The key thought in a control volume is you have mass coming in and or mass going out. That's what it is. Okay. Any comments or questions before we talk about specific heat? All right, well, let me make a little room here. We'll talk about specific heat. And then we'll work, after we study all this wonderful theory, we'll work some problems. All right, now the topic right now, we talked about this. Here, I'll put a little checkbox. Ta-da! We just talked about that. And now we're going to talk about specific heat. Now, this is in your book, and it's on page, let me find it here. I can't find it. Yeah, here we go. In my book, it's on page 89. And the topic is specific heat. Now the symbol for, there's actually, for gases, there's two of them. There's a CP and a CV for gases. But for solids and liquids, there's only one. But the symbol for specific heat is a C. Now, don't get confused. There's something called a specific heat transfer that we just talked about. Specific heat transfer. The symbol for that is the little q. See, heat transfer. This is a little confusing. See, heat transfer is a big Q. If you divide by mass, specific heat transfer is a little q. But specific heat transfer is different than specific heat. Well, I've tried to explain specific heat transfer and heat transfer, but what the heck are these things? Well, according to the book, this actually is a partial derivative. Unfortunately, it's the partial derivative of enthalpy with respect to temperature, and I haven't told you what enthalpy is yet. But this one here is the partial derivative of specific internal energy with respect to temperature. They're partial derivatives. Now, I'm not sure if you've all studied partial derivatives or not. But in case you haven't or you're rusty, maybe you've forgotten what they're all about. See, when you have something that's a function of more than one variable, like let's look at this one. That little u stands for specific internal energy. And if you go to the back, like for water, for instance, here, let me just find something here for water. I don't care what table you look at, but you need at least two things to find the little u there. Like for instance, here, I'll give you a for instance. Suppose you had water at 100 kilopascals and 300 Celsius. If you go to the tables in the back and you have H2O at 100 kilopascals and 300 Celsius, the specific internal energy is equal to 2810.41 kilojoules per kilogram. But before we go on, I need 2 or 3 students to tell me that they can find that in their tables. I'll shut up, and I'm waiting for 2 or 3 students that know how to go to the tables. This happens to be superheated vapor water table. Go to the table and see if you can find that. I'll be quiet for a minute until I'm going to hear from you. What we're trying to do right now is we're trying to see if you can look up in the superheated vapor table for water that has a pressure of 100 kilopascals and a temperature of 300, and the specific internal energy is 2810.41. Did I get it right?
Yeah, that's what I found.
Yay! Now, was that Roxana?
No, it was Megan.
I'll learn your voices eventually, Megan. It takes me a while. I need somebody else, though. I want to have confirmation on this. Megan and
That's what I
agree.
found as well.
Yeah. Now, who was that?
Stuart.
Stuart. Good going, Stuart. Good going. Now, did you notice that it required 2 things? It required the pressure, and it required the temperature. So you see, that little u there is a function of temperature and pressure. Let me write that. U is a function of temperature and pressure. Now, what they're doing is they're taking a partial derivative, but they're only doing it with respect to temperature, because it depends on 2 different things, but they're only taking the derivative with respect to one of the things. Now, it turns out that if you have an ideal gas, let me make a little room here where I can operate here. If you have an ideal gas, that the specific internal energy turns out to be a function of temperature alone. It doesn't matter about the pressure or anything else. But see, water is not an ideal gas. If I told you to find the specific internal energy of water at 300 C, if that's all I gave you, and I ask you to find it, you can't find it, because see, for water, it requires at least 2 variables to find the internal energy, specific internal energy. But did you know for ideal gases, like air, for instance, air behaves like an ideal gas. You don't need to know the pressure. All you need to know is the temperature. Now let me show you that. Go to page, see if I can find this. Yeah, here we go. No, that's not it. Okay, yeah, here we go. Just need a little room here. Everybody knows this is Wednesday, June the 10th. And everybody knows what we're studying here. We studied the first law of thermodynamics. And right now we're studying specific heat. We'll get to enthalpy in a minute. But I want to just show you something. Air behaves at the temperatures and pressures that we use for our work as an ideal gas. And the energy of an ideal gas depends only on the temperature. Now, if you go to table A.7.1, you can look up the internal energy for different temperatures. Like, for instance, if you have air at 300 degrees Celsius, the internal energy is, let me see if I can find it here. It's 214.36 kilojoules per kilogram. Now again, I want several of you to tell me you can find that. Find table A.7.1 for air and look up the specific internal energy for air at 300 Celsius. Can you find that? Can you find it?
I got the same thing you did.
Good going. And now, was that Stuart? That was Spencer, wasn't it?
Spencer.
Yeah.
Yeah.
Good. I need another student that can find
That's
that.
what I got too.
Good. Was that Roxana?
Aubrey.
That was Aubrey. Good going, Aubrey.
I found that too.
Yay, proud of you. Now, did you notice you didn't need to know the pressure, did you? Because, see, if you have an ideal gas, the energy is dependent on the temperature alone. So you don't need no stinking partial derivative. If you have an ideal gas, you can get rid of this partial derivative stuff and just make it an ordinary derivative. See, an ordinary derivative is like that. That's what you guys study in differential equations. You study ordinary derivatives. I think you have to go on to another class to get the partial derivatives. At least that's the way I remember it when I was in school. We had ordinary derivatives, and then another semester we had partial derivatives. So if you have an ideal gas, these are your what they call the specific heats. Okay, if you've made it that far, we're going to come up with some very useful equations now. If that made any sense, please ask me a question if you got lost on that. But if you're happy, I want to see if you can get to here with me. See if you can take that and write it like this. And this one, see if you can take it and write it like this. Can you guys get from here to here? You algebra students, can you make it? Now watch this. We're going to do a little tiny bit of calculus. Here we go. We're going to go meow, 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 meow. Now I know I haven't told you what enthalpy is yet, but we're getting there. But on this one here, you know what that is? That's just delta U. See, when you go from U1 to U2 and you integrate that, that's what you'll get. So we have a lovely equation here for delta U. It's equal to this right here. Now there's a catch. This only works for ideal gases. What if you don't have an ideal gas? If you don't have an ideal gas, we'll say something is not an ideal gas. Like, for instance, maybe water, for instance. Water's not an ideal gas, but see, air is. You can get the change in specific internal energy from air by doing this. But how do you do this? Let me ask a student. If you have something like water that's not an ideal gas, how are you going to find the change in specific internal energy? Let me pick on my friend Roxana. Roxana, take a wild guess, Roxana, and tell me if you don't have an ideal gas and you can't use this, something like water, how would you find this delta U, Roxana, for water? Go ahead, Roxana.
With the first law.
No, that's not the answer I wanted. See, teachers want the answer that they want. Now, the first law is going to use this delta U. The first law goes like this. And Roxana's right. There is a delta U in the first law. That was intelligent. Muy inteligente. But what if you didn't know Q and you didn't know little w there? How would you find this delta U for water, Roxana? Try again.
Maybe with the tables.
That's it. That's it. Good going. You would look it up in the tables. Exactly. Proud of you. You just go back there in the tables and you'd look it up. Now, the catch is you're going to have two things, like we talked about before. The temperature isn't enough. You'd have to have the temperature and maybe the specific volume. Those two would do the trick. You could find it. Or the temperature and pressure. Or you could even have pressure and specific volume. You have to have at least two things. And good going. You look it up in the tables. But if you have an ideal gas, you can use that equation. Now let me show you what you can do with that equation. Make a little room here. We got this equation now. Let me write it up here someplace. We're going to study enthalpy in just a minute. Okay, we've got this equation. Now this thing right here is called the specific heat at constant volume. That's how they measured it. It's pretty much a constant. Let me see if I can show you. It's not exactly a constant. It does change. Let's see if I can find this. Just a minute. Yeah. In my book, on page 92, I need more room to operate here. In my book on page 92, they have a graph. Basically what they're graphing is temperature. Well, they're graphing C sub P, but it would look similar to the specific heat at constant volume. Actually, they're dividing it by R, but don't worry about that. And for air kind of goes like that. There's a graph there for air. It kind of flattens out even more than that. It's pretty constant once you get out here to I don't know, 2000 degrees Celsius. See, it just doesn't change much. From 2000 to 3000, there's 3000. It just doesn't change much. The value is just in here someplace. It's pretty constant. If it's constant, you can pull it out and you can get this. Now, if you integrate that, you'll just get delta T. You get C delta T. And so here's our equation. Now that's C sub V. There's our equation. When we study enthalpy, you'll discover the same reasoning applies. And you'll get the change in specific enthalpy equal to that. If you have a liquid or a solid, for liquids and solids, these are approximately equal, and they're equal to C delta T. There's only one value of specific heat for liquids and solids. But for gases, there are two different values. These are the important equations that you will use. Now, there's exceptions I'll tell you about. But we've just talked about specific heat. Let's see if we can give you an example. Let's give you an example. You have any questions first? Okay. Suppose you had air, and you're going to go from 300 Kelvin to 400 Kelvin, and you want to know what the change in specific internal energy is. Well, according to this, you just go CV delta T. We got to look up CV. So go to the back and help me shop around and find this CV thing. I'm having trouble finding it. Aha, air, CV. It's 0.717. This is 0.717. Now this is table A.5. And these are kilojoules per kilogram Kelvin. Now the change in temperature going from 300 to 400, you know what that is? That's final minus initial. Hey, I could do that in my head. I'm getting 71.7 kilojoules per kilogram. Did that make any sense to anybody, you think? Can you find that table on the C sub B 0.717 on table A.5? Let me show you another way to do it. Now there's another way to do it. Instead of using the specific heat, they call this the specific, that's the name of it. That thing right there is called specific heat. It's very useful because it can give us these things here that we'll need. And like my wonderful student, I forget which one it was, mentioned, this here appears in the first law of thermodynamics. So it's important. You can get that from this. But there's another way to do that where they've actually integrated. See this equation here? They've actually integrated it, and it's equal to U2 minus U1. Well, they have a table of those. This is table A.7.1. Go to the back and find table A.7.1 and take the little u at 400, which is 286.49. And subtract the little u at 300, which is 214.36. Now I want you to go to table A.7.1 and see if you can find these numbers. I'm going to shut up for a tiny minute, because if you can't follow that, you're going to be lost. Look it up. Can you find those little u's? Can you find them? I'll pick on my friend Megan. Can you find those values? We're doing air now. We're doing air.
I'm still like looking for them
That's
in the
fine, man.
online book.
Take your time. We're going to wait because I want to make sure you can find these. How about my friend Cameron? Cameron, have you found those yet?
Yes, I found them.
Cameron found them. How about my friend Bear? Bear, have you found those yet?
I'm currently on the table.
That's fine. Look up 300 Kelvin and 400 Kelvin. And see if I got those U's right. Did I get them right, Bear?
Yep.
I heard a yep. Well, hopefully most of you are with me. Now see, I'm showing you two ways to get this delta U. Now this is important because it shows up in the first law. Remember, Remember the first law, the most important equation in the class. It's equal to this. It's in the first law. I'm showing you two different ways of getting it. Now, one way, we did it down here. We looked up this C sub B thing, and we multiplied, and we got an answer. Ta-da! Now, the other way is they have actually integrated this, and they have values for U2 and U1. Now, I'm going to subtract those and see what I get. Here goes. I'm subtracting now. Did I subtract correctly, students? I'm getting 72.13. Now we have two answers. Notice the answers are pretty darn close, aren't they? We got 72.13 here and 71.7 here. But those are pretty darn close. Now, one answer is a little more accurate than the other. They would both be okay on an exam that you took, but one is a tiny bit better than the other. Let me pick on my friend Aubrey. Aubrey, you got a 50-50 chance of getting this question right, Aubrey. One of these answers is better than the other. There's a 72.13 and there's a 71.7. Aubrey, which answer is a little better?
72.13.
That is correct. That is correct. You see, this answer here depends on your specific heat being a constant. Remember, we pulled it out of the integral. But I told you that it's not exactly a constant. It does change with temperature, not much, but a little bit to throw you off. So this answer is better. They've actually integrated this thing because it changed. See, that's why they invented integral calculus. If nothing ever changed, you wouldn't have to worry about integrating because this would just be a constant. But because it's changing, you have to integrate and you get a slightly better answer. Okay, well, I've shown you about the specific heats now, and these are terribly important equations. We need to talk about this enthalpy thing now. That's the next topic, and then we'll do some example problems. All right. Our topic right now is something called enthalpy. And it's defined, this is the definition. It's defined as U plus PV. That's the definition of it. Now, we're really more interested in little letters in our course. So here's what we'll have. There is no little p. P is pressure. There is no dividing by mass there. But see, if you divide by mass here, you get little u and you'll get little v. And divide by mass, you get specific enthalpy. Now, I mispronounce this. I'm not pronouncing this in the sophisticated way. See, when you go to get your PhD at Harvard, they pronounce it there as enthalpy. That's what they call it. They call it enthalpy. They don't call it enthalpy like your friendly Oklahoma community college professor tells you. But we're not at Harvard. But it's the same thing, whether you're at Harvard or whether you're here. That's what enthalpy is. Only they would call it enthalpy. I just thought I'd tell you that so you'll know when you hear that, well, what's that guy talking about? That's not what Mr. Griffin called it. Well, probably because they're doing it correctly. Well, so what? There you have it. That's the definition of it. Notice pressure is always positive. This is absolute pressure. It's always positive. It can never be negative. Now you can have a negative gauge pressure, but you can't have a negative absolute pressure. The smallest you can ever get is 0. Perfect vacuum would have 0 pressure. Now, specific volume is always positive. There's no such thing as a negative volume. You can go down to 0 volume, but volume's always positive. So this term is a positive times a positive, so it makes it a positive. You'll discover that enthalpy is always a little bigger than specific internal energy. Specific enthalpy is always bigger than specific internal energy. Okay, well, great. So what? Well, let's see if we can show you some things there. Suppose you took the derivative of both sides. I just want to show you something interesting. If you take the derivative of this and integrated it, I'm going to skip a step, but I bet you calculus students can get to here with me. The change in specific enthalpy would equal the change in specific internal energy plus better yet, we'll just leave it like that. We're going to throw in a little assumption here. Suppose you had an ideal gas. If you had an ideal gas, I think I'm skipping a step. Let me, if you have an ideal gas, you know what? P little v is equal to RT, isn't it? If you have an ideal gas. Now here's where I want to go, this delta H. Delta H is equal to delta U. R is just a constant. So that's equal to R delta T. Can you get from here to here, math students? I'll pick on, we'll go back to Stuart. Stuart, unmute. Can you get from here to here with the mathematics? You okay with that?
I believe so, yes.
Okay, well, good. Now watch this, Stuart. We're going to write down some stuff that we just came up with. We just talked about these equations. We came up with an equation up here someplace that said this here and this here. I tried to show you where those equations came from. And keep in mind now, those are only good if you have an ideal gas. If you don't have an ideal gas, do not use those. Here, let's put a skull and crossbones on these equations. They're wonderful equations, but do not use them for water, for instance. They don't work. Very good. Okay, now watch this. We're going to do a algebra trick now. See if you can get to here with me. Can you make it to there? But still picking on Stuart now. Stuart, can you get from here to here? Can you make it?
Yes.
Yeah, of course you can. Now, usually they write it like this. They usually write it like this, and we're going to see if this really works. Now for air, we'll go to the back and we'll look up some different stuff, okay? And go to the back. We won't do air, we'll do something else. How about helium? Yeah, here we go, helium. Now if you look up helium, you'll see this is 2.0771. This is 5. Guys, I'm on table A.5. Look on table A.5, and I'm just writing this stuff down. 5192. C sub V is 3.116. Now I'm doing this for helium right now. I'm looking up helium. Now take your calculators, and we'll see if they got that right. Let's subtract that. 5.192 minus 3.116. Boy, Jove. Well, I didn't get exactly what they got. Did I write those down right for helium? 5.193. No, wait a minute. This is 5.193, isn't it? I wrote down the wrong number. Let me get this right. Did I get that right? Okay, now I'm going to subtract those. 5.193, 3.116. Hey, that worked pretty darn good. I tell you what I got when I subtracted, I got 2.077. I didn't get the 1 there. But hey, look, if you only have 3 digits on these, you can't get 4-digit accuracy on that. Hey, that equation worked pretty good. That's a nice equation. And notice that these are kilojoules per kilogram Kelvin. These are kilojoules per kilogram Kelvin. And these are kilojoules per kilogram Kelvin. You know what? R, C sub P, and C sub V, they all have the same units. Let's do another one. I don't know if everybody was with me on that. Here's what I want you to do. I'm going to shut up while you do this. We're going to do air. I want you to find the R for air. And then I want you to find the CP for air. And then the CV for air. And then I want you to subtract the CV from the CP and see what you get. Now I'm going to shut up while you guys look this up. I'll tell you where it is. It's on table A5. Go ahead. I'll be quiet. I want you to do that. Okay, well, here's what I got. I got 0.287 kilojoules per kilogram Kelvin. 1004 kilojoules per kilogram Kelvin. And 0.717 kilojoule. I got these on table A5. Now I'm going to subtract those and see what I get. Here goes. 1.004 minus 0.717. Well, boy, Jove, I got 0.287 kilojoules per kilogram Kelvin. You know what? This equation seems to work pretty good, doesn't it? In other words, the gas constant and the specific heats are very much related, aren't they? Okay. Any comments or questions on that? All right. Well, I'm going to show you something else here now. If you're happy with all that. Okay, well, if you're happy with it, I need some room here to operate. I'm going to erase some stuff. All right. Now on your exam, I think your exam is available to you. You could be working on it. In fact, I think it's, isn't it due at midnight tonight? Is that right? I'll pick on somebody here. Mohammed, the exam, is it due tonight at midnight?
Yes.
I think it is.
Yeah, it's true tonight.
So, you better get started on it.
Yeah, I already started.
Yeah, I know you
guess.
have. I know you have. Okay, here, I want to show you something else. Now, this time, see, this works whether you have an ideal gas or a real gas. It doesn't matter. It could be a solid or a liquid. This is good for anything. So what I'm going to do is, I'm not going to have an ideal gas, but see if you can follow this. I think I was starting to do this earlier. This is just calculus stuff here. What I'm doing here is I'm actually taking the derivative and then integrating it. And I think the calculus students can get to here. What I'm really doing down here is the product rule. Remember the product rule? You take this one times the derivative of that one plus the derivative of that one times that one. That should ring a bell, product rule, calculus students. So you get that. But now what I'm going to do is I'm going to talk about a very special process. We talked about isobars, isobaric processes, didn't we? I know we did. I think we talked about isocores, isotherms, and isobars. Now, if you have an isobaric process, this term drops out. How come this term goes to 0? let me ask my friend Megan. Megan, unmute. Tell me if you have an isobaric process, why this term here goes bye-bye, Megan. Tell me.
I don't know.
That's a good, honest answer. Well, what would the change in pressure be if you had an isobaric?
Oh, it would be 0 because there is no change because it's.
She's got it. She's got, see, this drops out. Now this right here, if you have an isobar, that's going to equal little w. Let me see if I can show you on a PV diagram. See, if you have an isobar, you're either going from left to right, 1 to 2, or you're going from right to left from 1 to 2, but whatever it is, this area under here is equal to the little w. And you know what that's equal to? It's equal to the height of your rectangle times your the base of your rectangle. Well, the base of the rectangles, can you see that this term right here represents the work per mass for an isobar? We'll still pick on my friend Megan. Megan, can you see that this term represents the work per mass?
Yes.
Yeah, yeah. Okay, now watch this. I got one more step and then we're going to come up with a really nifty little result here. All right, now keep in mind though that what we're doing only works for isobars. But now isobars are important because your condenser and your evaporator on your air conditioner on your car, those are isobaric processes. You like to be cool when you're driving around this summer, and the evaporator and the condenser on your air conditioner are isobaric. And so they have to obey this equation right here. And now watch this. We're going to do a little bit of algebra here. I'm going to replace this with Q minus W. Now you have to add the little w to it. Now how come I'm still picking on Megan here. Megan, how come, why can I substitute Q minus little w for this delta U? Megan, why is that legal to do that? How come delta U is equal to Q minus little w? How come?
Because that's the first law.
Yes, it's the first law. And now watch this. We're going to do some algebra now. I'm getting the change in enthalpy is equal to just Q because these go bye-bye. Can you see that? Ooh, nice little result. What this says is, now the catch is that there's a skull and crossbones on this. Do not use this equation unless you have an isobar, because otherwise it's no good. But if you do have an isobar, and you have a couple of them in your air conditioner in your car, the heat transfer is equal to the change in, the heat transfer per mass is equal to the change in specific enthalpy per mass. And this is what you're paying money for. You know what that costs you money? It costs you money to keep your car cool. Did you know that if you don't run your air conditioner, you get a little better gas mileage? Let me pick on Bear here. Bear, did you know you get more gas mileage if you keep your air conditioner off? Did you know that?
Yes, I did.
He knew that. He knew that. It costs you money to keep cool. Well, your refrigerator, you want to keep your eggs cold and your milk cold. It costs you money to do that. But so it's important. I mean, money is important. So this heat transfer is important. They call that heat transfer per mass. That's the name of it. Let me write that down. That's called heat transfer per mass. And it's equal to the delta H, where that's the change in your specific enthalpy. Okay, well, that's pretty fascinating. Now that doesn't have to be ideal gas. We never said ideal gas. It could even be a liquid. But now, if it is an ideal gas, if you do have an ideal gas, then this is equal to C sub P delta T. But if you don't have an ideal gas, well, you can't use this equation unless you have an ideal gas. If you don't have an ideal gas, what do you use? Now, let me ask my friend Aubrey. Aubrey, if you do have an ideal gas, you can use this equation. What if you don't have an ideal gas? If there's no ideal gas, how do you find, Aubrey, how do you find your delta H if you don't have an ideal gas? Go for it, Aubrey. What do you do?
Is it change in U plus pressure times delta?
Well, no, Aubrey is correct. Aubrey is correct. It's equal to it's equal to this, right? Yeah, that's what I was trying to write there. And if you had a what's the word, a isobar, then it's equal to that. But the answer that I wanted, see, teachers have answers that they want. The answer I wanted, Aubrey, is if you can't use this, you use the tables. You just look it up in the tables. See, there's H's in the tables. Go back here to the tables, any old place, flip any place, and you'll see little H's all over the place. And that's, instead of doing this, you just go H2 minus H1, you look it up and write it down. It's real easy. Okay, well, great. Do you have any comments or questions on the stuff we've studied? We've studied the first law, specific heat and enthalpy, and we're going to work some problems now. But before we work the problems, did you have any questions or comments? Well, okay, we're going to take a 10-minute break. And in 10 minutes, we'll work some example problems. And now you have homework. I don't think your homework is due till, gosh, I think it's next Monday night. I give you till the next class session, I think. Is that right? Can somebody tell me if you look up the homework for tonight? I can look it up, but I'm too lazy. Let's go to my friend Spencer. Spencer, there's some homework that you guys are supposed to do for me. When is it due?
We have assignment 3 from last time that's due tonight, and then assignment 4 over what we're learning today that's due on Monday.
That's correct. You got it. You have homework that's due tonight, and then you have, gosh, Don't you have the test due tonight too, don't you, Spencer?
Yes.
Man, I kind of overloaded you there, but it wasn't that hard. You'll be all right. And then the other homework, you don't have to start on it till, I don't know. Let's see, it's due. What's it due? Monday? Is that what you said, Spencer? Monday?
Yeah, Monday night, midnight.
At midnight. So if I were you, I'd start working on it long about 10 p.m. on Monday. That would work. Okay, we're going to take a 10-minute break. Go stretch. I'm going to stretch. And then I'm going to do some sample problems with you guys. Okay, 10-minute break. We'll be back. Go stretch. We'll be back.
Professor Griffin.
Yeah.
I can't find the test on Blackboard anywhere. And someone said that it looks like it's been removed.
And is this Megan?
Yes.
Anybody else out there tuned in? And can you hear Megan has a problem finding that test?
I just looked through as well, and it looks like it's not there anymore.
It's not there anymore. It was there and now it's gone.
Yes.
Megan will check into that and we will make some kind of arrangement.
Okay.
Some of you got it. A bunch of you got it, didn't you? And some of you, you can't find it.
I can't find it either.
Now, who is that?
Bear.
Bear can't find it either. Kind of hard to do a test if you can't find it, huh, Bear?
Little bit.
It makes it tough. Well, I wonder why it would disappear like that. It's supposed to disappear at midnight tonight, is what it's supposed to do. Maybe I can go in there and change the disappearance to tomorrow night. That might give you some more time. But I'll work on that. I promise you guys. We'll make that test available to you. But the thing is, some of you have it. Some of you have had it because you've emailed me and said, ask me a question or two about it. So I'll figure it out. We'll have to extend the time on it, but we will give you guys a fair chance to find the test. I don't know what happened, but we'll figure it out. Do not panic. Do not change your major. We will figure it out. Okay, well, let me go ahead with our wonderful lecture. And the problem I want to do right now is problem 398. It's dealing with air, which we can treat as an ideal gas. And it's isothermal. Now let me find it here. And we'll work that thing out about the test. I have no idea what happened. But we'll figure it out. I think to find that test, you have to go to Blackboard, and you have to click on Unit 1. And I think you click on Assignments to get to it. Try that.
It's not there anymore. It was there on Monday, but it's not there anymore.
How weird. Okay. Well, right now we're doing 398. And I appreciate you guys telling me. We'll work it out. 398. Piston cylinder device has 1/10 of a kilogram of air. Let me write this stuff down. 1/10 of a kilogram of air at 300 K and 100 kilopascal. The air is now slowly compressed in an isothermal process to a final pressure of 250. Okay. We're gonna up the pressure. Let's draw our PV diagram. Now, the key to solving these problems in this class is a PV diagram. Now, if you're dealing with air, you don't do that vapor dome, because see that vapor dome has got saturated mixture where you have part liquid and part vapor. Well, you don't have part liquid and part vapor. It's just all vapor because it's an ideal gas. But now 300 K is a curve like this. And these curves on your ideal gas PV diagram, they have a fancy name. I will pick on, I'm always picking on Stuart. Have you noticed? Stuart, what's the name of this curve for an isotherm on an ideal gas? Go for it, Stuart.
Is it a hyperbola?
That's it. Good going. Good going. Stuart, listen to me. I like that when my students listen to me. It's called a hyperbola. Yeah. Now we're at 100 kilopascals, so I'll just say here's state one, and here's 100 kilopascals. And we're going to go to, if you read the problem, 398, got lost here. If you go, we're going to go to 250 kilopascals. So 250 is up here someplace. 250 kilopascals. There's state two. And here's your process. You're going to go from 1 to 2. That's your process. There's a 1, there's a 2, and you have an arrowhead on the end of your process, and we're going to follow that isotherm. And they want to know the work and heat transfer. Okay, well, that's what they want to know. They want us to find the work and the heat transfer. Okay, well, why don't we draw a device sketch? Here's state one. There's your piston cylinder for state one. And this is going to be state two. Oh, I think I'm going to sneeze. I'm not sure, but I think it's coming. So I thought I'd warn you. Do you notice that the specific volume is getting smaller? So we're compressing, aren't we? We're compressing. And oh, look, the pressure is going up. So it's like somebody put a heavy weight on here. And so it made it go down. Okay. Well, that's kind of what it looks like. All right. Here's state two. Now, when you do that, when you compress things like that, they usually get hotter. I don't know if you've ever, say, pumped up a bicycle. Take a bicycle pump, and you pump, and then feel it. it kind of warms up. When you compress a gas, the gas gets hotter. But see, we're not getting hotter. We're staying the same temperature here. Now, to do that, the only way that's going to work is you're going to have a heat transfer out. See, that's what they want us to find. They want us to find this heat transfer out. Now, the work, here I'll pick on Spencer. Spencer, the work going from 1 to 2 is either going to be positive or negative. And now you're compressing, and I've told you this several times, but Spencer, is the work going to be positive or negative going from 1 to 2? What do you think?
Trying to remember.
Take your time. He's looking it up
Is
in
the
his
work
notes.
negative when it's compressing?
That's right. Yay. Yay. Good going. The work's going to be negative. It's going to be negative because you're compressing. See the environment. See, somebody put this heavy weight on here. That's in the environment. Here's our stuff that we're talking about here. There's a certain amount of mass of air in this case inside this piston. And you have the same mass of air inside the piston here, but somebody has put a heavy weight on there. That's in the environment. The environment is doing work on the system, and that's negative work. See, if the system does work on the environment and lifts the weight up, that's positive work. So we now know the answer will be negative. What about the heat transfer? We'll pick on somebody on that now. Now we know that the work is going to be negative. And now we're going to talk about the heat transfer. Let me pick on Mohammed. You got a 50-50 chance of getting this right, Mohammed. Is the work or is the heat transfer going to be positive or negative? What do you think?
I think positive.
It's positive?
Yeah.
You missed it. You missed it, Mohammed. I'm sorry. You had a 50-50 chance and you blew it. No.
Negative.
That's
I
okay.
mean,
That's okay. Now, see that the heat transfer is going out. See, heat transfer going in is positive. But I think you're going to have a heat transfer going out. Otherwise, the thing would get hot. But it's staying the same temperature. In order to stay the same temperature, you have to have a heat transfer going out. See, that heat transfer is going out. So the heat transfer, we think, is negative. Okay, well, they want us to find that. Now, how are we going to find that? I got an idea. How about we try this here? Now, that equation has a name, and we've been studying it today. And let me go to my friend Megan. Megan, are you one of the wonderful students that's having trouble finding that exam?
Yeah.
Well, we're gonna fix it, Megan. Just we'll get it. But Megan, my question to you right now is, this equation it's a very important equation, and it has a name. What is it?
The first law.
Yay, good going for you. That's exactly what it is. Now, last time I showed you how to get this little W. We went through it. If you had to, you could look at the YouTube video over again. But we had an equation. If I remember right, it went P1 V1 natural log of V2 over V1. I'm still talking to Megan here. Megan, Do you remember us doing that for an ideal gas isotherm? This equation works for an ideal gas isotherm. Is it my imagination, or Megan, did we talk about that last time? And did we come up? I think I derived it. I think I derived that
Yeah.
equation. Did we?
Think so.
I think we
Or
did. I forget what we did to get at it. Oh, I remember. What we did was little w is equal to the integration of P dV. It's the area under this graph. And I showed you how to do that. And see, I forget what we did though. I think what we did was PV equals RT, where this is a constant. See, it's a constant. And I took that and I substituted, I integrated it, and I came up with this equation.
that sounds about right.
I think that's what we did. Well, anyway, we can get this little w because we know P1. Oh, we don't know V1. Okay, well, let's see if we can find it. Now look here. P1 V1 is equal to R T1. Well, we know T1. It's 300. Here, let me write. Megan, what does it mean in this class when I circle stuff?
We have it.
We have it. T1 is 300. Now, P1 is 100. See, we know what P1 is. And we know what R is. So we can get V1. So I'm going to shut up for a minute and a half. And I want you guys to get that V1, and then we'll proceed. On your mark, get set, go. Find V1 for me. Well, let me pick on another wonderful student. Bear, have you got that V1 yet, Bear?
I'm still plugging things in.
Plug away, it's fine. Well, there's no big hurry. How about my friend Aubrey? Aubrey, do you have this little V1 for me yet?
I got 0.861 meters cubed per kilogram.
Gee, you have your volume turned way down?
I don't think so.
I can barely hear you. Tell me what you got. What'd you get?
0.861 meters
Holy
cubed
moly.
per kilogram.
Holy, the volume suddenly got real loud. Yeah, that's what I got. Well, now looky here. we now know V1, ta-da, we know V1. If we could only get V2, we could get that little W. Well, look at here. P2V2 equals RT2. Now we know T2, it's 300. We know R, and we know P2, it's 250. So now we're going to get V2. Again, I will shut up. I want you to find V2 for me. Go for it.
Would it be 0.5542?
That's not what I got. Now, I could be wrong, but I'm getting 0.3444. Let me do it again. I could be wrong.
But as well.
No, I think that's right. Now, who got 0.5 something? Who was that?
That was me.
Is that Spencer?
Bear.
Bear. Bear, go back and do it again. Okay, guys, we got everything. Look at here. We can get our little W now. I'm going to plug in P1, V1, natural log, V2 over V1. We got this equation last Monday, and we're going to get little W. Here goes. Well, I got a value for the work per mass. I'm getting a negative. Remember, we said it was negative. We said the work was negative, didn't we? Now watch out, we got a negative in our first law, but the value itself is negative. So you're going to have two negatives there. Now get this delta U. We're going to use C sub V delta T. And we know what delta T is. What is the change in temperature? Let me pick on my friend. Back to Stuart. I'm always picking on Stuart. Stuart, what is the change in temperature going from 1 to 2?
0.
It's 0. It's, you know what this is? This is 0. So we have 0 equals Q minus 78 point blah, blah. So I tell you what the Q is. I just need a little room here. I think that the Q and the little w are equal and they're both the same. They're negative 78 point blah blah. But that's not what they wanted. They wanted big Q and big W. Now to get that, you just multiply by the mass. See, big Q is equal to M times little q. Big W is equal to M times little w. So when you multiply by the mass, you get negative 7 point, here we'll round it off. Ta-da! That's it. We have just solved for the heat transfer. It's negative 7.89 kilojoules. And the work, it's negative 0.89 kilojoules. And we have drawn our device sketch. We have labeled the heat transfer there. Temperature stays the same. We never labeled the little V's there, but we could. See, this one's 0.861. And the other one's 0.3444 cubic meters per kilogram. So there we have it. We've just done problem 398. I think we did pretty good on that. Well, we're going to work some more problems. But before we do, take a good look at that and make sure you're okay with it.
Why was the delta U 0 again?
Oh, thank you for asking. Delta, that's such a good question. Delta U is equal to C sub V delta T. Now, was that my friend Megan? Is that who that is?
Yeah.
Megan, Megan, what is the change in temperature?
Okay.
You got it, don't
It's
you?
yeah, it's temperature stays the same. Okay, that makes sense.
You got it. But that was a good question. I'm still listening for any other comments or questions. Okay, well, we're going to do another problem then, if you're happy with this. Are you starting to catch on to the method of solving problems in this class? The key is this PV diagram. It's the key. But this thing here is important too. Now, this has got a name. What do they call this? Let me pick on Spencer. Spencer, what do they call this right here? This, it's got a name, Spencer. What's it called?
Which part were you pointing at specifically?
These two. I've got two cylinders here with pistons, and this whole thing here is called the It's called the What do they call it, Spencer?
I'm not entirely sure. Did that have something to do with the compression?
Let me write it for you. This here is called the device sketch.
Okay.
It's the device sketch. See, this here is called the PV diagram. And the key to solving problems in this class is the PV diagram and the device sketch and this equation here. Spencer, what's the name of this equation right here?
First law of thermodynamics.
Good going. It's the first law. PV diagram, device sketch, first law. That's how you do it. Okay, well, let me erase this. We're going to do another problem. If you guys are happy, I'm still listening if you have a question. All right, well, we'll say goodbye to that one. And we're going to do problem 363. Now, 363, let me find it here. Okay. We're dealing with R134A. That's what you have in your car. You have R134A in your car air conditioner. We've got 2 grams. Oh, I'm sorry, 2 kilograms of refrigerant R134A at 350 kilopascal and 100 Celsius. Now, I want you guys to write this stuff correctly. That's how you write a kilopascal. You don't go kPa. That's not how you do it. You don't go kPa. That's not how you do it. You don't go kPa. That's not how you do it. There's different ways of doing it wrong, in other words. Let's do it correctly, okay? Now, correctly, it's a little k. That stands for kilo. You don't use a big K. Big K stands for Kelvin. Don't use big K. And then there's a big P and a little a. Let's do it right. Okay, now let me keep reading. We're going to do 363 cylinder frictionless piston to superheated R134A vapor. It's now cooled, so the R134A remains at constant pressure. All right, now what we're going to do is we're going to make a PV diagram. Now this is R134A, and you're going to have a vapor dome. It's going to look like that. And I want you to go to the tables now and find R134A. Go back here and start shopping around till we find R134A. I found it. This is table B.5. B.5.1. And I'm just going to try to find my bearings now where we are. See, there's a critical isotherm that comes here through here like this. And this critical isotherm is 101.2. 101.2 degrees Celsius. And that pressure there is 4064. It's 4064 kilopascals. Now, I want everybody, I want everybody to look up on table B.5.1 and see if you can find the 101.2 and the 4064 kilopascals. I'll be quiet while you look. See if you can find it. And then I'll pick on Mohammed. I'm always picking on Mohammed. Mohammed, unmute. Can you find 101.2 and 4064 on table B.5.1, Mohammed? Can you?
I'm looking for it.
That's okay. Take your time. Take your time. Mohammed's trying to find that table. Let's pick on Megan. Megan, have you found that table yet? Unmute.
Yeah, I found it.
Did you find the 101.2?
Yes.
Good going. How about the 4064? Did you find that?
Yeah.
Great. I just did that to sort of orient myself. That's not where we're at, guys. We're at 100 Celsius. See it? Well, you know, that's awfully close to 101.2. That would be just hugging it, wouldn't it? It would be just hugging it. Real close. This top one's 101.2, but this one's 100. We're someplace on that 100. Now we need 350 kilopascals. Well, gee, that's a lot smaller than 4,000. I mean, 350 is way the heck down here someplace, folks. Does that make sense? If that's 4,000, 350 is down here. So that must mean that we are located, bingo, there's state one right there. We're at 350 kilopascals and 100 Celsius. There's state one. Okay, let's keep reading and see what we're supposed to do. We are doing problem 363. It says the cylinder is cooled so that the R134A remains at constant pressure until it reaches a quality of 25%. Well, 25% quality, that's in here someplace. So here's what we're doing. We're going from 1 somewhere in here. We'll call this 2. Now, I don't know where 2 is exactly. But keep in mind that these are logarithmic. They're not linear. So it could be, I don't know, it could be here, 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 here. I don't know. But it's got to be isobaric. Read it. It says it's cooled at constant pressure until it has a quality of 25%. Okay. Well, now what we're going to do is we're going to look up the properties. It's state one. This is in the superheated vapor region. Remember, there's superheated vapor, there's saturated mixture. State 1's in superheated vapor. We know what T1 is. T1's 100. We know what P1 is. P1 is 350 kilopascals. Let's get little v1. Now, little v1, you're going to have to go to the superheated vapor table to find it. It's in superheated vapor. So flip your go to 350. Uh-oh. They don't have a 350. They have a 300 and a 400. But that's easy. It's just halfway between. So what I'm going to do is I'm going to take my calculator and find halfway between these numbers. And here goes. I'm going to do it now. Okay, I think this is 0.0596, blah, 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 cubic meters per kilogram. But I want to give you guys a moment to find that. Now, this was on table B.5.2. I found this on table B.5.2. I want to see if you can get that. I'm going to shut up for just a minute, and I want to see if you can get that. I found the specific volume at state 1. Can you find it? And I'll pick on my friend. I forget where I am on my list of people to pick on here. We'll go with Aubrey again. I think I've bothered Aubrey several times, but she's come through for me. Aubrey, were you able to get that? That 0.059, blah, blah, blah?
Yes, I was.
Yay! You had to divide by 2, didn't you?
Yeah.
Good going. Okay, well, great. Let's find the specific internal energy at state 1. I got to do the same thing, Aubrey. They don't have a 350, so you're going to have to go in between 300 and 400, and I'm going to do that at 100 degrees Celsius. Okay, here it goes. I'm going to divide by 2 here, 460. If anybody needs me to, I can write this out. If you don't have any idea, what on earth is he doing now? If you're totally lost, I'm getting 460.56. I bet that's right. Kilojoules per kilogram for the specific internal energy at state 1. But if you want me to, just say, Mr. Griffin, write it out. And I'll wait. If I hear those words, Mr. Griffin, write it out, I'll write it out.
So I'm a bit confused on how that specific volume was found.
Let me write it out.
0.059.
Oh, okay. Let me write that out for you. Now, was that Spencer?
Yes.
Okay, Spencer. Here's what you do. You go to table B.5.2.
Right.
And you look up 100 Celsius. And here I'm going to write it out for you, Spencer. It's 0.07325. And at 300, it's 0.9809. Yeah. I might have made a mistake here. I don't know, but we'll see. 0.9861. And then you have to divide by 2 because we want 350. See, they have 300 and 400. Did I get the right numbers written down? Yeah, I think those are the right numbers. Okay, now I'm going to add those and divide by 2. Here goes. 0.07325 plus 0.09861 divided by 2. I didn't get this number. This is wrong. Spencer, I don't know what I did. Spencer, did you get 0.8593?
I did. I tried using the ideal gas method before, and
No. Can't use
that wasn't right, but it was closer to this.
Yeah. I don't know what I did, Spencer. I pushed the wrong buttons, and I'm going to give you a thank you point for calling that out. Guys, don't let me. I'm horrible about this. I'll push the wrong buttons and get the wrong answer. But if you'll stay with me, we'll get that. Now, how about Spencer? How about the specific internal energy U1? Did you get that number? Did I do it right?
Oh, I haven't gotten that far because I'm still trying to figure out where I went wrong on the other.
You didn't go wrong. All right.
That was my problem.
I want you to get that for me. I'll be quiet. You guys might want to make a paper copy of those water tables. We use them all the time. Unless you're particularly good at computers. I like the paper myself. Spencer, did you get that U1?
I can't find the equation I need to be using.
Oh, well, here, let me write it out for you. Spencer, at 400 kilopascals and 100 Celsius, it's 460.22. We're using the tables, table B.5.2.
Oh yeah, just the average.
It's just the average. And then the other one is 460.90 at 300 kilopascals. We want 350. Divide by 2. You should get this right here.
Yeah, I got that.
Yay. Good going. So we got U1. Now here's what we're going to do, guys. We're going to go delta U equals Q minus W. That's what we're going to do. Now, delta U is U2 minus U1. We just got U1. There it is. Ta-da! And you hopefully understood what I did. Now we're going to get U2. Okay. We're going to get this now. Here goes. We're on table B.5.2 right now. And to get U2, what you do is you go UF plus 0.25. I showed you this equation. In fact, I think we derived it. I forget which day it was. It might have been a week ago. But we can look those up, see? UF is, now you got to go to the saturated table, what I call the vapor dump table. And you have to look up 100, no, you have to look up 350 kilopascals. Well, guys, they don't have a 350 kilopascals. They have a 350.9. That's so dang close to 350. I'm going to use that. I'm going to use that. I'll be very teeny tiny amount off, but it's close enough. We'll be all right. And here's what you're going to have. You're going to have 206.48 plus 0.25 times 174.38. You need to be on table B.5 in order to find those numbers. I want you to go to table B.5 and find those numbers. And I'll pick on, let me pick on Megan again, but I'll give you time. I'll shut up, Megan, and let you see if you can find those numbers right there on table B.5. See, what we need is 350 kilopascals. They don't have 350, but they have 350.9, and that's what I'm using, Megan. I'm too lazy to interpolate. I don't think it's going to make that much difference. Megan, were you able to find those numbers right there? The 206 and the 174 on table B.5? Actually, it's B.5.1, isn't it? Table B.5.1.
I'm still looking.
That's okay. Take your time. We need the pressure of 350. They don't have 350. But they do have.
Okay, I found it.
Good. They have 350.9. See that there?
Yes.
That's what we're going to use. And then you write down the UF and the UFG. There they are. And now we're going to get U2. Here goes. Guys, I think I know what U2 is now. I think U2 is 250 kilojoules per kilogram. And we have U1. I don't know where it went to. There it is. So U1 is 460. So we have both of these. And we're going to finish our problem now. They want to know the work and the heat transfer. Okay. Well, let's get this. Let's do the work first. Here we go. Now the work going from 1 to 2, that's just the area underneath this graph. See this big old rectangle here? That's little w, isn't it? Okay. I'm going to get that little w. Here goes. Little w is, well, it's a rectangle. The area of a rectangle is the base times the height. I know we can do that. Okay, little w is the base. Uh-oh. We never got V2, did we? We need V2. Did I do V2 and no, we never did it. Never mind. We got to get V2. No problem. We're just going to go to the 250, is it? Is that what we want? I got lost. I had a senior moment. No, it's 350. There you go. So V2 is going to be 0.0000783 plus 0.05755. Well, you go 0.25 times 0.05755. 0.05. See if you can find these numbers on table B.5.1. B.5.1. We're trying to get little v2. See, I need this little v2 down here. I've got little v1. It's right here. We got, no, that's backwards. I've got little v1. It's right here. Ta-da. Little v2 is this here. Can you see where I got those numbers? I got a bad feeling I'm going too fast for some people. See, I'm trying to find the area of this rectangle. I know how tall it is. It's 350. So if you want the area of that rectangle, you go 350. That's how high it is, times the width. Well, I need to know what this is. Let me get that. Well, if I did that right, little v2 is 0.01517. So we think we know what little v2 is. It's 0.01517. And we know what little v1 is. It's 0.08593. So we should be able to get the base of your rectangle, and the height is 350, and the base is 0.08593 minus 0.1517. So we can get the little w. Here goes. I'm going to do it now. All right. Did you get the work done is a negative 24.77 kilojoules per kilogram? We think we got the little, we think we got the work done per mass. And we can get this because we have both of those. We have U2 someplace. I don't know where it went. Where do U2 go to? There it is. It's 250. And we have U1. We have U2, we have U1. And we can get, guys, if we know what U2 and U1 is, we can get this. And if you know what little w is, we can get the heat transfer. Okay. I got a bad feeling I might have lost somebody. Bear. How lost are you, Bear?
Surprisingly, only a little.
Oh, that's good. Just a little bit lost. Good. Good, good, good. Well, let's write this stuff out. I just need some room to write it. I know what U2 is. It's, it took me a while, but it's 250. So let me write that down. $250 kilojoules per kilogram. That's U2. U1 is 460.56. Q we don't know yet. There's a negative sign in the first law. And the work, we figured the work. It's around, yeah, here it is. It's negative 24.77. So we could get the heat transfer. Let's do it. Here goes. I'm plugging all this stuff in. I'm getting a rather humongous heat transfer of negative 235.3. I've worked this out and I've checked the answer. Let me make sure that's right. I might have made a mistake here. I don't know. I've got it here someplace.
I worked W to be positive 24.77.
Well, it can't be positive because you're compressing. See, your volume's
okay.
getting,
I
yeah,
see.
it's got to be negative. Okay, now let me find my my key here someplace. I wonder what I did with my key. Let's see. This is 363. $363. Okay, I've worked this out before and I got negative 24.7 something for the work. Well, where's the work? Yeah, that's correct. Negative 24.77, that's the work. Now the heat is negative 230, that's correct, 235.3 kilojoules per kilogram. That's the heat transfer per mass. That's right. Now they wanted big letters. They wanted big W, which would be the mass times little w. Well, okay, we can do that. Now what did they say the mass? Oh, it's just 2 kilograms. So you just take 2 kilograms times the 24. I could almost do that in my head. Get around 48, right? Only if you take 24.77 and multiply it by 2, you get the work done is negative 29.54 kilojoules. Oh, gee, we only have 5 more minutes. I wanted to show you something else. We might have time. Now let's do the big Q. The big Q is m times the little q. Well, see, that's a little q, so you have to multiply by 2 to get the big Q. 235.3 times 2. I'm getting negative 470.6 kilojoules. You don't go per kilogram because, see, you multiply by kilograms. You understand? And kilograms times kilojoules per kilogram just gives you kilojoules. So there's your answers for the work done. They're both negative. You know what we didn't do? We didn't do the device sketch. Let's do the device sketch. And then we're going to have to quit. It's sad, but our time together is coming to an end. I need some room to do the device sketch, so we're just going to make some room. Here we go. We're going to make some room. Here's state 1. And here's state 2. Now, state 1, you're out here like this. Having trouble drawing a straight line there. And you're out here in superheated vapor, remember? And all you got is vapor. There's no liquid. But now at state 2, you're 25% vapor and 75% liquid. So you're down here someplace. But you haven't added any. You haven't added any weight to it because the pressure is the same. This is an isobar. But now look, you've got some liquid. Some drops condensed on the sides and dribble down here. And you've got liquid and vapor. It's a saturated mixture. So you're in the saturated mixture, but the pressure is the same. Can you see you compressed? So you know compression work is negative. Look, it's negative. Work is negative 29 kilojoules. And now the heat transfer is negative. I usually put my heat transfers in red. So you've got a heat transfer out. It's pretty big, actually. It's transferring at 470 kilojoules. Now, why is it transferring out like that? It's condensing. Condensing is the opposite of boiling. Now, if you went the other way, if you go from saturated mixture to superheated vapor, that's boiling. And you know to boil, the heat transfer will be positive. Here, let me make a note of that. If you want to boil something, the heat transfer is going to be positive. That makes sense, doesn't it? You put water on the stove and you turn on the fire and you wait a while and water gets warmer and then it starts bubbling and steaming and boiling. You have to input heat transfer in to boil, but see, we're not boiling. We're condensing. Condensing the heat transfer is less than 0. See, it's negative. There's a heat transfer out to the environment. And in fact, what will be the temperature there? It was 100 Celsius, but what is the temperature there? Well, let's look it up. At 350, oh gee, we're about out of time. It's so sad when you're having fun, the time just goes quickly. I'm trying to find this R134A and find the temperature, and then we're going to have to quit, I guess. R134A, I'm looking for it. Ammonia, carbon dioxide, R134A. Hey, I found it. I found it. And remember what we wanted was 350 kilopascals. Well, we don't have a 350 kilopascals, but we have a 350.9. And guess what the temperature there is? According to the table, it is 5 degrees Celsius. So here's your isotherm. And it goes like this. It's 5 degrees Celsius on table B.5.1. You can look it up. B.5.1. We went from 100 degrees Celsius to 5 degrees Celsius. It's 5 degrees Celsius. Kind of cooled off, didn't we? Well, how do we do that? Well, by having a heat transfer out. That makes sense. Well, our time together has come to an end, and I'm going to work on this exam and make sure you have time to work on it. Any last comments or questions before we say goodbye? Anybody? Comment or question? Well, okay, nobody said anything. Unless you speak up, I'm gonna blast off here. Here's your last chance to make a comment or question. 5, 4, 3, 2, 1. Blast off.